I'm Downey. I teach computer science. I'm a professor of computer science at Olin College, which is a small engineering college in Needham, Massachusetts, just outside of Boston. I'm going to be talking today about hypothesis testing, which is a standard topic in a statistics class, but the way it's usually taught is what I call a menagerie of tests, which is that you see t-tests and f-tests and z-tests, and students might pass the exam at the end of the class, but what I see a couple of years later is that when they have to apply a hypothesis test to real data, they tend to be paralyzed. They vaguely remember that there were a lot of tests, and they remember that each test had rules for when you were supposed to use it and how to test to make sure that you're using it correctly, but they don't remember any of the details. So often I see on conversation boards like Reddit that people will come on and they'll ask, what test should I be using? Should I be using a one-sided test or a two-sided test? What are the requirements? If my data are not normally distributed, will the test work correctly? What's the minimum sample size that I need? These are typical of the kinds of questions that I see. And usually what happens is that I'll talk to the author of one of these questions, and what I find out is that the real problem is not just choosing the right test. The answer is not, you should use a z-test, go. What's usually going on is that the person asking the question hasn't really figured out what the hypothesis is that they're trying to test, and they don't have an explicit idea about what the null hypothesis is. And I'll talk about that in just a second. Now, I know that if any of my slides have a cartoon, that you're not going to be listening to me, so maybe I should just read that one to you. The scientist is saying, I've narrowed it to two hypotheses, it grew or we shrunk. The other problem that I see is that often if you apply a standard test, and especially if you use a software package, it cranks out an answer. And at the end you have, let's say, a p-value of 0.06. The problem is that unless you have a good understanding of what produced that number, you don't have a lot of confidence that that you asked the right question or that the answer is meaningful. So these are the problems that I've seen, particularly when I'm trying to help people work with real data. And what I found myself using over and over is this framework for doing hypothesis testing. And since it's the same framework every time, I now think of that as being, there's really only one test, and it looks like this. In the top left corner there, that's your real data. You've run an experiment, you've collected a data set, and now you've got some test statistic that you compute. So for example, if you have two groups and you think that they're different in some way, maybe you compute the difference in their means. And that difference is what I'm going to call delta star. And the star means that it's the actual value that you observed. What I'm going to recommend as a way of doing hypothesis testing is simulation based on a model of your null hypothesis. So if you read across the bottom row there, H sub 0 is the null hypothesis. That's the assumption that there's not really any effect going on here, and that the apparent effect that you saw is just due to chance. So the question we want to ask is, what's the probability of that? What's the probability that I could see an effect as big as what I saw purely by chance? So if you're a programmer, the natural approach to this is to write a small simulation of the null hypothesis and use it to generate some fake data. And that's what those little rows of simulated data are. If you now apply the same test statistic to your fake data that you use for the real data, then you're going to get this distribution in the lower right. And that's, what would the range of values be for delta with my fake data, purely due to chance? And now that shaded area on the right is the p-value. That's the probability of seeing an effect as big as what you saw purely by chance. So that's the overview of everything that I'm going to talk about today. If all of the details aren't clear yet, hold on a minute, I'm going to do an example. So this is an actual post that someone put on Reddit, I think it was a month or so ago. asking about an experiment that they had done and how to analyze it. And it says, as part of a college course, we gave a class of students a pre and a post test to judge how well the students knew the material before and after the class. I would like to know what type of test to run and what I can justifiably infer from the data. And then there's some details about the experiment. We have 30 students who took the test twice, before and after. Each test was 50 problems, and the students received a number grade with the corresponding percentage score. So my standard recommendation whenever I see a question like this is before you do any testing, you need to get a sense of what your data set looks like. So you need to do some exploratory data analysis. Usually I would start out with some summary statistics. So I'd like to know, what was the mean score on the pre-exam? What was the mean score on the post-exam? And right off the bat, I'm going to get a sense of whether there's likely to be an effect going on here. If those two numbers were identical, I would be skeptical that there's going to be anything interesting to find. The next thing I would do more generally than looking at summary statistics is to plot the entire distribution of scores. That'll give me a sense of the shape of the distribution, whether it's roughly normally distributed, whether it might be skewed to one side or the other, and often, importantly, whether there are outliers. The next step, since we're doing a before and after test, would be to go through each student and compare what was the change for that student. So I would take the pairwise differences of the post and the pre-exam scores, and I'm going to call that capital D for the whole talk. So for a given student, the change in score for that student is capital D. I'd also want to look at the distribution of D. So that would be my first step, is to just look around at the data and make sure that I have a general sense of what it looks like. The next step, as I said at the top, is you need to be precise about what the hypothesis is that you want to test. So the natural question to ask here is whether the students learned anything, right? You offered a class, you would like to believe that the exam scores would be higher at the end than at the beginning. But there are different ways that you might make that more precise. You might want all the student scores to go up. You might be satisfied if most of the students improved. You might want to know, did most of the students improve by a certain amount? And there are other summary statistics that you might look at. I mentioned you might look at the difference in the means. Sometimes if there are outliers, the median might be a better statistic to look at, or there might be other percentiles that you're interested in. Part of the reason I want to talk about this is that at the same time that you're making your hypothesis more precise, you're also choosing what your test statistic is going to be. And what I mean by that is you have to boil down the size of the effect to one number that corresponds to that size. So what we have right now is for each student we have a capital D. That is how much the test score changed for that student. Natural thing to do would just be to take the mean of that. So what that would say is that the mean change is, let's say, 2 points. So if on the first exam the average score was 36 out of 50, and on the second exam the average was 38 out of 50, you've seen a difference of 2 points. And the question now is whether that apparent effect is statistically significant. And that's what I'm going to call the $525,000 question. It used to be the $64,000 question, but I had to convert it into $2011. Here's what it is in words. What are the chances of seeing an apparent effect as big as what we actually saw purely by chance? The result of that is going to be the p-value. And the hard part of answering that question is when we say by chance, what do we mean specifically? That's what the null hypothesis is. Again, I'll let you read the cartoon. It says, I can't believe schools are still teaching kids about the null hypothesis. I remember reading a big study that conclusively disproved it years ago. And that's from xkcd. We're going to be coming back to another xkcd cartoon later on. What the null hypothesis is a model of the system under the assumption that the apparent effect that you saw is not actually real. So in this case, the hypothesis we're testing is that the students learned something. So the null hypothesis is the opposite of that. It's the assumption that they didn't actually learn. And so the question we're answering is, if that's true, if the students didn't learn, then what's the probability of seeing an observed value of delta that's greater than or equal to 2. Now, I said that the null hypothesis is a model, and what that means is that we're going to have to make some modeling assumptions in order to be more precise about what it means. So here are the assumptions that I'm going to make. The first is that for each student, there's this number, PC, which is the probability of getting an answer correct. So PC is probability correct. The idea is that there's an infinite number of possible exam questions that I could ask, and any given student has some probability of answering a randomly chosen exam question correctly. So under the null hypothesis, the students don't learn anything, and that means that the value of PC for each student doesn't change from the pretest to the post-test. Now I can generate exam scores because for each exam that the student takes, the score that they get only depends on the PC for that student and the number of questions that are on the exam. So now I have a model of the null hypothesis. And the next decision I have to make is whether to compute p-values by analysis or by simulation. And I've tipped my hand here, and I've said that I'm going to encourage you to use simulation first, and then possibly come back to analysis as a second option. And I'm going to explain why, but the primary reason is the solutions that you get analytically are often based on some simplifying assumptions, and if you violate those assumptions, there are some pitfalls that you can fall into. The nice thing about simulation is that you mostly don't have to think about those pitfalls. So it's I think, less error-prone. It's more flexible in the sense that we're going to be able to extend it to handle lots of different test statistics, lots of different scenarios. And I claim it's easy, although I have to put a qualifier on that, which is that if you're a programmer, if writing a small simulation is something that you think is easy, then I think this approach is easy. So I'm going to recommend simulation. Here's what the simulation is going to look like. For each student, let's assume for a second that we know what the value of PC is. So we're just going to generate a random score for the first exam, generate another random score for the second exam, compute the difference for each student, that's the capital D, and then take the average of those differences, and that's the delta. And let's say that I do that 1,000 times, then I can just count how many times I see a simulated value of delta that's greater than or equal to 2. And this idea, the nice thing about simulation is that you are computing probabilities, but you're computing them by just counting the number of times that something occurs, which is in some sense the most natural definition of what probability is. I've got a picture of Francis Galton there, who's one of the early statisticians, and this is actually his quote: "Whenever you can, just count." So I want to bring the framework back. I talked about this at the beginning, so to review, I'm now working across the bottom row. I'm going to start with a model of the null hypothesis, generate simulated data, and then compute a p-value. Now there's one more assumption I have to handle before I can do this, which is that I said we have to know the value of PC for each student. And if we don't know that, and we really wouldn't know that, we're going to have to do something reasonable as a model of the null hypothesis. So one possibility is to just take the scores from the pretest and treat them as if they are a perfect picture of the value of PC for each student. So if a student got 50 out of 50, I would say that his value of PC is 100%. And if he got 25 out of 50, then I'm going to say that his value of PC is 50%. An alternative is if I have a reason to believe that the distribution for the class has a particular shape, then I could simulate that distribution and just draw a sample from it. Okay. So I'm going to show an example of this using some code. I'm going to use Python, so if that's familiar to you, that's great. If it's not, I think the code is simple enough to be readable. So the first function I'm going to use is called flip, and it's going to take PC as the parameter. So for any given student, let's say that they have a PC of 50%. This is going to flip a coin, and it's going to return the value 1, with probability PC and 0 otherwise. So you can think of that as being a single question on the exam, and it's returning the number of correct questions. Now I'm going to use flip in order to write fake exam. So fake exam is going to simulate one exam. It's going to take PC and the number of questions on the exam, and for each student it's going to return a randomly generated number of questions that they answer correctly. So in the long run, a student with a higher value of PC is going to get better exam scores than someone with a lower value, but on any particular run, it's a random number and it's going to vary. Okay, now that I've got fake exam, I'm going to write another function called fake difference, or fake diff. It takes the same parameters. It takes the PC for a student and the number of questions on the exam, and it generates two fake exams, one for the pre and one for the post, subtracts the exam scores and generates a difference, so that's the capital D. Okay, now that I've got fake diff, I can write fake diffs. This now takes PCS, which is the PCs. That's going to be a list of values for PC, one for each student. So the length of that list will be the same as the number of students. And it's going to generate one difference, one capital D, for each student, and it's going to return a list of those differences. So this simulates running the entire experiment, giving a pre-test and a post-test to each student. And then the last function is the one that actually computes the p-value. It's going to take a number of iterations. In this case, I did 10,000, which is probably more than I really need. For each iteration, it's going to do a simulation of the whole experiment, and it's going to compute the observed value of delta, which is the average of all the Ds for each of the students. And you'll see the line that says, if the mean of the differences is greater than or equal to delta, then I'm going to increment a counter. So I'm really just counting the number of times that I would see a difference as big or bigger than what I saw, purely by chance, that is, under the null hypothesis. I run this program, and the answer turns out to be 0.007, which is a little bit less than 1%. So what that says is the probability of seeing this effect by chance is small, and the conclusion that I can reach is that if it's unlikely to have occurred by chance, then that's evidence that the students actually learned something, which is good. That's what we would expect to see after teaching a class. Now, we have to be careful about what the p-value is and what it isn't. So the p-value is the answer to one very specific question. It says, what are the chances of seeing what we saw by chance? And if that probability is small, then we conclude that, in this case, the students probably learned. But it doesn't actually tell us how likely it is that the students learn, so we don't have a probability for that without doing some more work. And it doesn't really tell us anything about how much they learned. If we want to do that, we have to do an estimation problem, and that's a different statistical method. So that is a p-value, and that's how at least I interpret it. If you've taken a statistics class, you might have heard different interpretations of the result of a hypothesis test. There's a little bit of controversy about this that I'm not going to talk about too much. But you've probably heard about significance levels. And it's often a threshold value. Very often it's 1 in 20 or 0.05. And the threshold is the line between something that's considered significant and not. So if the p-value turns out to be less than 0.05 or 5%, then people would say, yes, statistically significant. And if it's higher than that, then they would say, no, not significant. I want to argue against that a little bit. I don't think there's a magic line here. If you think that 4.8% is significant and 5.2 is not, then you're taking these p-values much too seriously. We went through a modeling process to get this p-value, and we had to make a number of decisions that were maybe not arbitrary, but certainly not determined by the data. So we had to choose which test statistic we were going to use. And I had a list of possible statistics. We had to make a model of the process where students answer questions, and we had this quantity PC, all of those modeling decisions affect the value that we're going to get when we compute this p-value. So I don't think you can count on a p-value being accurate to more than about a factor of 2. I like to think of it as having 0 digits of precision. What really matters about the p-value is the order of magnitude. So if the order of magnitude is 1% or less, I'm inclined to call that statistically significant. That means that the chances of seeing what you saw are less than about 1%. If the p-value turns out to be greater than 10%, I'm comfortable calling that not significant. That means that 1 time out of 10, you're likely to get fooled. And then in between, which is where this magic threshold usually is, I think anything in that range, from about 2% to 8%, is I would consider borderline. I wouldn't draw a strong conclusion based on that. Okay, a natural question you might ask at this point. I walked through a fairly long process on what is normally considered a pretty simple problem. And I said this was going to be really easy, and maybe you're thinking that it's not all that easy. I should be careful about what I mean by easy. We still had to do a lot of work. We had to think carefully about what the hypothesis was, we had to choose a test statistic, and we had to build a model of the null hypothesis. So yes, you still have to do some thinking about this, but the reason I think it's a good idea is that the thinking you have to do is exactly about the problem. You're thinking about the domain, you're thinking about your hypothesis. Those are meaningful questions. What you didn't have to think about was statistical esoterica. So going back to the question as it was originally posed, it was, which test should I use? And should I worry about violating the assumptions of the test? Those aren't questions about the problem domain. Those are questions about statistics. And I think those are harder questions to deal with than the kind of thinking that we had to do. So my summary is, don't think about 1,000 different tests and which one you have to choose. Really, there's only one framework for doing hypothesis testing. And you don't have to worry very much about things like your sample size or whether the distribution of the data violates assumptions. The simulation method that we just used takes those things into account. So if the sample size had been small, that would naturally have changed the p-value that we computed in the simulation without really having to think about that. The other objection that you might hear to doing this kind of simulation is that it's slow. You might notice I had to do something like 10,000 iterations in order to measure a p-value. If you do this analytically, the nice thing about that is that it's computationally efficient. And in fact, that's the primary reason that those analytic techniques were developed, is that they were developed before the availability of computers. So computation used to be very expensive, and analytic techniques used to be very important. Now, computation is very cheap, and I claim that simulation is at least a good place to start. Here's my 4-step process that I recommend for this. If you start out with a simulation, you might find that it just runs fast enough. So maybe it takes 10 seconds, or maybe it takes 10 minutes. If you only have to run it once, that's fine, and you can just stop. You're done with the problem. If it turns out that you need to apply a specific hypothesis test over and over, so if you've got a stream of data coming in and you need to handle these tests very quickly, then it makes sense, I think, to start looking for analytic shortcuts. And the nice thing is that when you do, you can use your simulation as a regression test and make sure that you're getting consistent results from both of them. So here's my argument. I think that using the analytic techniques is an example of premature optimization. And this is a quote from Donald Knuth. He was a famous computer scientist, and he said that premature optimization is the root of all evil in programming. Okay. I also said at the beginning that this technique is more flexible than analytic techniques. Let me give an example of what I mean by that. If you wanted to use a different test statistic, so instead of the mean of the differences, if you wanted to substitute in practically any other function, you can do that in the simulation by making one change in one place in this program. Just replace the mean with any function of the diffs. And that's going to work correctly in this framework because as long as you're using the same test statistic for the real data and the fake data, then you're making a valid comparison between the simulation and the real data, and your p-values are going to be meaningful. So with simulation, it's very easy to swap in a different test statistic. With analytic techniques, it's not nearly so easy. One last example I want to do, one of the problems that comes up a lot in real-world problems is not that you want to do just one comparison, but that you have a lot of groups that you want to compare, and it's tempting to do multiple tests to see whether any of them are statistically significant. But there's a danger there, and there's a nice xkcd cartoon that demonstrates exactly what this danger is. So this is going to take me a couple of slides to get through. But the first frame, someone comes in and says, jelly beans cause acne. So the scientists investigate, and they find that there's no statistically significant difference between, let's say, people who eat jelly beans and people who don't, and it cites that the p-value is greater than 0.05. So there's that threshold of significance. Someone comes back and says, but wait, it's not all jelly beans, it's only certain colors that cause it. So the scientists have to go back, and now they have to do a series of t-tests where they're checking to see whether each color of jelly bean causes acne, and they find for, let's see, purple, brown, pink, blue, teal, no statistical significance. Salmon, I don't know if there are salmon-colored jelly beans, but red, turquoise, magenta, yellow, none of these are showing statistical significance. They keep running tests. Oh, sorry, I think I've been showing you the wrong slide. Let me make sure that we're all on the same correct slide. Okay. These two slides look the same, so it's not easy to tell that they're different, but the key frame is number 4, where they find a statistically significant result between green jelly beans and acne, and the punchline is that the news media picks up that result and reports that with 95% confidence, we can say that there's a significant effect here. And there's only a 5% chance that this result would have been purely due to random chance. Now, the error here is that if you run a test 20 times, and each of those tests has a 5% chance of producing a false positive, then you expect on average that you're going to get about 1 false positive. So the right question to ask, if you're running multiple tests, the right question is not, are any of these tests significant? The question is, if I run 20 tests or 100 tests, what's the probability that I would see an effect as big as what I saw? Now, there are a couple of approaches to correcting this problem. Some of them are based on analytic techniques, and the Holm-Bonferroni method is one way of doing this. I've got a link to that in the slides, or you can just Google it. But there's an alternative, which is that you can take this framework that I'm recommending and extend it in a natural way to handle multiple tests, which is if you run all the tests, each test produces one test statistic, so you can take that result as one big vector of test statistics. And now you need to boil that vector down to a single number that's a measure of the size of the effect. So one natural possibility is that you could take the maximum of all the test statistics. You could take the mean. Actually, you could take any norm of that vector, which is why I have a picture of norm in case you were wondering. And so now the right question to ask is, if I run 20 tests under the null hypothesis, what's the chance that the largest test statistic exceeds delta star, which is the actual difference that I saw, actual test statistic that I saw? So that's the last example that I want to do now. I want to point you to a couple of other examples. I've written a couple of blog articles about this that also talk about chi-square tests and other test statistics that you might use. And this is also Chapter 7 of ThinkStats, so you're certainly welcome to check that out. And that's all I've got for now, so let me throw it open to questions.
Alrighty, folks. Now's your time. Now's your chance. Please send in your questions if you have them for Alan and what he has been showing you while we still have him. And we do have one question that came in from Ann Julie, and she asks, what paper should we cite if we want to use simulations to compute p-values in a scientific publication?
That's a good question. So, I mean, this is a general enough technique that I think there's not one source that you could point to. I think it depends partly on the venue that you're writing for, whether you need to go into details about how you computed a p-value. So, for example, I think it's legitimate if you cite a difference between two groups. So we measured the height of men and women, and we found that the difference on average is 2 inches. And then in parentheses, you could write p less than 1 in 1,000, or p equals 0.0007, or whatever it comes out to. Depending on the venue, you might not need to say how you computed that p-value. In other cases, you might say, p-value computed by simulation is estimated to be whatever it is. In other cases, you might have to spell out your methodology in more detail. And rather than cite a paper that says, here's how you do simulation, I think in that case the best thing to do would be to just make the code, whatever the program was that you used to estimate that p-value, just make that code available to people who are reading your paper.
Great. Let's see here. I'm not seeing any additional questions, but we'll give folks just a moment. Folks, again, if you have questions for Alan and what he's been talking to you about today, please type those into the group chat, send those in, and he can answer those while he is still with us. And as we give it just another moment here, Alan, is there anything in closing that you wanted to tell our audience about today? Maybe a little bit about your book?
Sure, I'd be happy to. So I mentioned that what I'm talking about today is Chapter 7 of ThinkStats. The subtitle of ThinkStats is Probability and Statistics for Programmers. And the underlying assumption is that if you already know how to program, you can use that as leverage to learn about concepts in probability and statistics. It's also, I think, a powerful technique for doing statistics, which is that a lot of the things that are difficult analytically are very easy to do computationally. So we talked about hypothesis testing today. That's one example. The other example that I used, and this is in Chapter 8 of ThinkStats, is Bayesian estimation. In most ProbStat classes, that's considered an advanced topic. It might not be covered in an introductory class at all. It might be in a graduate class. Doing Bayesian methods analytically is moderately difficult. The mathematics is sophisticated. But doing it computationally, I think, can be very straightforward. And so in Chapter 8, what I tried to do is present a framework similar to what I was talking about today, where you can do Bayesian estimation computationally without really having to think too hard. So I'd encourage you to take a look at that, and maybe that'll be a topic for a webcast in the future.
Wonderful. And we do have somebody asking if you could please tell the audience what is the URL for your blog.
Sure. It is, actually let me bring that up so I get it right. There's a link in the slides. It's on my second to last slide, so let me bring that up. And it is Alan Downey, all one word, .blogspot.com, and that'll take you to the home page. And there are links to all the past articles there.
Oh, wonderful. And it looks like Gilbert has a question for you, Alan. He asks, what math books would you recommend to relearn math, algebra, geometry, calc, trig, etc., for someone who hates being a human calculator but loves theory?
That's a great question. I'm not teaching math at that level, so I don't have good recommendations. I have to say most of the textbooks that I see are these enormous tomes that I find almost unreadable, and that's the reason I started writing my own textbooks, is that I was so unhappy with them. I have to admit that when I'm researching a math topic, I go to Wikipedia very often, and I go to MathWorld, which is run by Wolfram Research. Those are probably the two online resources that I use most often. But Wikipedia is written at a fairly sophisticated level of mathematics, so that might not be a great one for review. Let me take this question offline and see if I can find some good sources, and maybe there's a way that we can come back with an answer later.
Perfect. Thank you so very much. That looks like all the questions I see coming in. So folks, at this time we will conclude our webcast. We will say a big thank you to Alan.